welcome to a special guest here. We've got Doug Wibben from Benchmark. Doug, it's great to have you here. Thank you so much for joining us.
Yeah, no problem. Thanks for having me. I appreciate it.
So it should be. I mean, Doug, you've been with us really from the just about the beginning in terms of our odyssey of building this thing. And anytime if folks see the Oxide rack, and anytime you think of just the gorgeous mechanicals in this rack, it is Doug and his team to thank for that. They really, Doug, you did such a terrific job at. I mean, just so many junctures. I know we must have been just a little bit bonkers to work with, but really, really appreciate all you've done for us. One thing I was trying to remember is when we were initially talking with you, had we already figured out that we wanted to blind mate the networking, or was that after we had started speaking with you?
That was the first 3 months or so, a feasibility study to prove that it was possible. And then
Right.
from there, it was the plan of record moving forward.
Right. So okay. So we were already wondering if that was possible by the time we,
Yes.
because I think that, and that would have been right when we first started talking with you, because the story here is kind of interesting, that and Adam, I can't remember if you were on any of those early calls or not, but we were very much assuming that we were going to have, in terms of the networking of the rack, that we were going to have a traditional architecture of power and fans in the rear and having networking out the front. And when we were we were kind of surveying the industry and talking to various folks, making various connectors and so on. We were talking to one company in particular, and they understood what we wanted to go do, and they were, out of curiosity, why are you not blind mating the networking? Like, why are you doing this whole thing of the cabling out the front? And there was kind of this moment of like, I do the hyperscalers blind mate the networking? No, they don't blind mate the networking, but that's because they're afraid to blind mate the networking, which of course is just like catnip to us. It's like, okay, wait a minute. That's exciting. So when we just were immediately asking the follow-up questions of like, is it possible to blind mate the networking? Because, and by blind mating, we should explain what we mean by that. Yeah. So this is having the networking connection where you can't see it effectively in the back of the cubby, such that when you slide the sled in, it magically mates with the networking. There would be no user visible cabling in this kind of system, which we found really intriguing if it was possible. So we kind of had and I think it was at sometime at this point that kind of Arian had an initial sketch of, based on maybe this is feasible. Arian put together an initial sketch, and I'm going to drop this photo album, Adam, into the chat if you haven't already. So
I have not.
Okay, there we are. So and someone in the chat asks, "Are you aware of the Open19 networking?" And yeah, we were aware of Open19, and the Open19 uses this really interesting big connector in the back. And when we talked to people who talked about Open19, this was like the thing that was most interesting to them about Open19. 19, by the way, not for 2019, but for 19-inch rack. So we were aware of that, and and that was interesting to us. So this idea of there's Arian's early sketch that Adam dropped in, and boy, if we could actually put together the rack and blind mate networking, that was terrific. But is it feasible? And Doug, this is kind of where your team came in, and I mean, you began to inform us that this is definitely feasible, but here are some of the things that we need to look after when we are designing this thing. So what were some of the kind of the problems that you had in mind as we were beginning to design this?
Sure. So initially, coming up with a concept that would allow the gimlet to dock into the rack in a manner such that it would align mechanically in X, Y, and Z with the cabled backplane, pending our vendor selection. That was a difficult task. The Oxide rack is primarily sheet metal parts, and sheet metal fabrication is one of the less exact fabrication processes for mechanical items. So in figuring out how to make that work, we had to go through a lot of mechanical tolerance analyses to determine how best to approach that.
It's occurring to me that I'm going to be getting fears that you had that I never had. I'm actually realizing that I'm going to come away with this conversation with a whole new set of both appreciation for what you all have done and newfound fears. So you were concerned about, in particular, sheet metal imprecision in terms of getting this thing to line up properly.
Correct. So, between the latching system on the front of the gimlet, which had yet to be designed at the beginning, and the uh, cassette or cartridge at the back of the cubby, there are something like 15 or 20 mechanical dimensions contributors to the overall tolerance stack, which have to be combined and accounted for to make sure we're making the appropriate connection at the rear, physical connection at the rear.
Doug has said gimlet a couple times, just for folks who have not listened to the show as in a detailed fashion over the years. Gimlet is the code name for our server that sits in these cubbies that Brian was alluding to. So when you hear gimlet, that's the server that slides in.
That's right. And so the concern that I know, and Doug, I remember we talked about this early on as well, having been with backplane systems in various parts of my career, one concern you always have is around bent pins. And then of course the very worst case of that, the bent pin virus, where you have something with bent pins that is bending whatever you plug it into. And if you start moving that around, you can actually start bending a whole bunch of pins. And Doug, your team did a terrific job in terms of engineering how to prevent someone from bending the pins. Do you want to describe how you pulled that off?
Sure. So it started with connector selection. We assessed a number of different suppliers and looked at the physical makeup of the connector and tried to kind of judge what we felt the capacity for bent pins would be on any given design. So we moved forward with the connector design, which we thought had the lowest potential for bent pins, and kind of moved forward from there into integrating it into the mechanical design. So we use probably more rigid steel mechanical guide pins than we need in aligning the connectors. But again, given the concern and the challenge of correcting, finding and correcting bent pins, we wanted to kind of, if we were going to over design any part of this mechanical design, that would be the one to over design. So, just I don't know how deep we want to go from the start.
Yeah, actually, I mean, a couple of things are interesting there. One, I love your exciting. We so emphatically agree that if you're going to have a system, an aspect of the system that you over-engineer, you got to figure you're going to over-engineer, under-engineer everything, right? And maybe you're going to perfectly engineer some things, but basically you're going to solve for problems that you maybe will never have. And then, of course, we don't want to, but not solve for problems that we do have. And in terms of when you describe, because this has been a very thoroughly solved problem, and boy, is this a good place to thoroughly solve a problem, because the consequences of this are pretty high. It's pretty expensive, because the connectors are expensive, obviously the sleds are expensive, and the steel pins are relatively cheap. In terms of what this actually added to the BOM cost and so on.
Correct. The steel blades are $1 or $2. So yeah, in terms of overall BOM costs, it's minimal.
And you can, we always joked back in the day, we called Adam Leventhal hardware engineer for his various hardware engineering exploits as a software engineer. And Adam, as I recall, it was a key part of Adam Leventhal hardware engineer was the running start.
That's right. That's right. And actually, it started with unbending some sheet metal. That, I don't remember this, but an early design for one of the head units of the Fishworks storage product was such that you couldn't actually insert a PCI card without quite a running start.
I do remember this. I
definitely, Doug's right. Like, that sheet metal really gave it up quickly. Like, I didn't really bend the heck out of it.
And Adam, I don't know how much time you spend moving the sleds in and out of the game, but it's extremely satisfying with all of
it. Really is. Yeah.
The guide pins. And it doesn't matter if you take a sled, it really doesn't matter how hard you ram that thing in, because you're going to be caught by this mechanism that Doug and team designed. Doug, do you want to speak a little bit to that mechanism? I don't think we'll put a photo of it. I don't think we've got a photo in the album, but we'll create a photo of that mechanism. Do you want to just describe a little bit how you did that?
Sure, I'll describe it the best I can without a photograph. But basically the gimlet, the server latching system on the front has a rotating handle, and based on feedback from you, Brian, and similar experiences from Adam and the like, we wanted to make sure that this running start was something that we had a safeguard for in the mechanical design. So as you're pushing the server sled into the rack, the cubby, it actually bottoms out on a welded steel pin on the latch before the connectors, less than an inch or so before the blind mating connectors for power and the signal in the back of the gimlet are able to connect to the cable backplane in the rack. So if you get, the proverbial running start, you stop on something before the second stage of insertion kind of takes place. When you lift the handle, then it starts to more gently and with a kind of decreased mechanical travel engage and dock the connectors at the rear. So again,
Yeah, and
not completely bulletproof, but we tried to remove as much of that capacity to occur as possible.
well, and I just think, I mean, as with so many aspects of the system, but Doug, this is something that you definitely got from us very quickly. Is we've all tried to bring our collective wisdom into the system, and obviously, you and your team brought a lot of your collective wisdom, and I think it shows when you feel the thing. It's like, okay, someone has had the same kind of problems that I've had. Someone has had the person in the lab taking the running start or had to take the running start. So there's a lot of thought has gone into how this connection is actually made. And could you talk? I mean, Doug, I know that there were some of these terms that were very new to me. Things like gather and the way these things actually, the connectors actually mesh. What are some of the things you've got to think about as you're designing that?
Sure. So the free end of the connector on the cable backplane in the rack has a steel, a pointed steel guide pin on it, and also used in conjunction with the metallic blades that we've got on the floating cartridge. Um, Depending on the angle of the point of this pin and the lead in on the receptacle, you've got what the connector manufacturers publish as gather. I don't remember the exact number for these XMX connectors we're using. I believe it was between 2 and 3 millimeters of gather. So that means your connector on the back can be misaligned by up to 2 or 3 millimeters, and it will still kind of find its home and align itself for the final kind of docking of the connector. So the connector system itself, the first maybe 1/3 of engagement is purely the guide pin mounting or mating with the guide hole on the opposing connector pair. And then the last, half or 2/3 or so is actually the the wafers and the blades and the other electrical interconnect occurring. So when we designed our kind of floating interconnect system at the back, given this is blind mate, we knew fairly early we couldn't rigidly mount these cable backplane connectors to the rack, to the cubbies, or again, with sheet metal tolerances stacking up, the potential for, misalignment and for things to actually engage was extremely low. So we designed a floating system so that within the cable cartridge that attaches to the back of the cubby floats mechanically. I believe it's up to 2 millimeters to allow the system to kind of gather itself within this published gather of the connectors themselves. So I guess in short, our mechanical stack of tolerances had to be below this 2.9, I believe, gather millimeters of gather of the connector in order for us to ensure that we would always make contact.
And the consequences of getting this wrong. I mean, you obviously have the mechanical consequences in terms of things bending or breaking, but then you presumably just have the consequences of just not having enough contact for a good signal. What are some of the consequences of getting this wrong?
Correct. So in kind of the X and Y, I'll call it, not the depth of the server. That's where the gather is impactful. So you want to make sure vertically and horizontally, the connector is aligned such that you're catching it, you're docking it um, appropriately, and then basically as long as you're within that gather to start, once things start to fully mate together, they align themselves by virtue of the alignment pins and come together in kind of that X and Y. The other dimension, I guess I'll call it Z, basically the depth of the server as you're looking at it from the front. That's a kind of a different metric in that regard. We wanted to make sure the connector was fully mated within reason as much as possible. So if these connectors are mismated, basically not plugged all the way in, there is some signal loss, I believe.
Right. Yeah.
So the connector family that we're using is fairly forgiving in that sense. I believe it's 1 or 2 millimeters allowed to still not have a significant signal loss. However, we wanted to make sure in the connector design, the connector system design, that we always kept this as low as possible. So I think worst case, we could have a 0.5 millimeter mismate, basically not fully engaged. And then we've got a spring system in our connector so that when the connectors crash into each other, um, the one pair on the rack just floats backwards within the tolerance of the spring. So there's kind of some intentional collision there by design, which helps us ensure that we are, as mated as closely as possible within that dimension.
Yeah, and someone in the chat said like it sounds like it's docking a space capsule, and it does. I mean, it feels like that. You've got a lot of degrees of freedom, and you need to be sure that you've designed for all of these things to not damage one another. And then that's not good enough to merely not damage one another. You actually need to make this really this tight tolerance with respect to a contact. And just so people know, like, how many connectors are we talking about here? Because people may be thinking, like, I don't know, how many pins are there? 10? It's like, no, we got quite a few more.
So there are 3 connectors per server, not all of which are used, and each connector has 8 wafers of 4 pairs, differential pairs. So I think we're looking at around 1,000 pairs of I/O, somewhere in that neighborhood, all of which need to be connected for the system to fully work. So
Holy
yeah,
smokes!
it's
I,
no
I
small.
I had no idea the number was that high. Now, Doug, is that high? That seems extremely high. Like,
Doug, in your
I mean,
professional opinion, are we
what I
crazy?
mean is like what is like that seems like high for the industry, like a bold direction. Is that or are there instances where there are even higher connector counts?
That's a great question. I'm not aware of any, but I don't know that I have the depth of experience there.
it's pretty dense.
Yeah.
I mean, XMAX connectors are, if you're looking for a high density blind mateable connector, like you're not going to really get other connectors that can do that. I mean, you can get other connectors that are not blind mateable that all have, you can get high density, but for where we're at, like, yeah, this is pretty dense.
It is, and yeah, because I think it's, and you look at the back of these connectors, and it looks like a hive of the connection. I mean, there's just a lot, and then Doug, I assume I mean, there's also you're going to have a lot of mechanical resistance when you go to plug that in, and so you also need a way of like getting that in, allowing someone to do it easily, be able to make that connection without having to get a running start, without having to. So there's a lot going on here.
There is. So this connector family, the insertion force is fairly low. I don't have a number off the top of my head, but in terms of the overall percent contribution to the Gimlet server docking, I think it was less than 50%. The the mechanical friction of steel on steel is a fair contributor as well. But the handle has roughly a 3-to-1 mechanical advantage to kind of assist this, to make the last bit of the docking, of the two-stage docking, a little more friendly for the user on the outside end.
Yeah, definitely, and ends up being. And it's so we obviously need to not just plug and unplug these things all day, because these connectors do have a limited lifetime in terms of the number of times you can plug and unplug them, which is a good thing, because otherwise I might do exactly that. It's so satisfying to plug these things in and unplug them. One of the questions folks are asking is like, well, can you just use RJ45 cables? And you really can't at this speed. So this is all 100 gig, and we actually wanted to be able to go. We wanted to actually be able to get not just 28 gig NRZ, but be able to get to 56 gig PAM4 potentially on the backplane. And maybe this is a good segue to how we actually think of that backplane. And Robert, do you want to maybe intro your favorite design partner in terms of Samtech?
Well, would I ever? Yeah. So, I mean, there's a lot of, well, actually, I guess there's not like too many different vendors you can go with when you're looking for different types of connectors or interconnect solutions. And particularly when you're going with like standardized components, you kind of get funneled into maybe like 2 or 3 people, really. But there's, another vendor that does a lot of really specialized stuff, and then a lot of bespoke, like specialized but general purpose industry. So like the AXMAX connector, for example, is something that's shared between like Amphenol and Samtech. Amphenol made it, but Samtech uses it, and that's kind of special for what we're doing, but it's pretty general connector. And then they make a bunch of really special stuff that a lot of, say, you would see on FPGA boards, which have like mezzanine cards that need like 500 pins in this really dense row. And then you come across this company, Samtech, that can like let you customize all of these things in all the different ways that you want. And you just build it on their little website. And then they have this little button that says, "Would you want a sample?" And you can click it and they'll send it to you overnight. And it's amazing. And you can do that for anything you want. And they'll just do it. And then you're like, how can these people afford it? And why would they be so kind to me? And then they email you and ask you, "Hey, I saw you did this in this little, design. Do you need any help? Like, can we get our SI team to help you with the model that you need in order to do the breakout on your bullseye cable that you like just randomly ordered?" And you might think, yeah, actually, I would like some free help.
I would like.
Isn't that amazing? And they, then you find a vendor. You're like, you give a shit? Oh, I want to work with you. And turns out that they do care, and they will send people to your manufacturing plant to help you figure stuff out on the fly. It's pretty great. Like, who are these people? And I've used them before, and there's so many other things that I could talk about that they just like totally saved my ass. But they're amazing. And so we, after we're having trouble with another vendor, like, when organizations get big and you kind of have difficulties, then you're not a really big customer. So you kind of run into the problem where maybe they can't make things happen as quickly for you, and they don't want to devote the time that, otherwise they would. And so I asked, maybe we should go with Samtech, because I've had this experience in the past where they've been so extremely helpful, even though, you could be kind of a nobody. We should at least ask. And so we did, and lo and behold, they like deployed in force to help us build this thing that they looked at and said, "Oh, sure, yeah, we can do that," and no one else wants to do it. And so, be our pilot. Sure, we'll do everything that you need. And they helped us build this entire system, kind of hand in hand, which was, kind of incredible, because we're just buying products for them, right? They are not an investor. They're not like, we do super well. It looks good for them because we use their stuff, but like they have no skin in the game, really. But it didn't matter. They went well and beyond what they needed to do in order to make us successful. And behold, the backplane, integral to the product.
Totally. And it's always, they're a very engineer-driven company, and they really know how to make engineers happy. And they with technical engagement and technical support, but then also I mean, I think that for us, and Doug, I think part of the reason our relationship with you has been so great is like we're looking for fellow engineers who want to go solve an interesting problem, solve a hard problem, solve something that's commercially relevant. And not everyone has that disposition. You get to some folks who are like, "Why are you doing it this way?" It's like, no, because we think this is a better way to do it. And with Samtech, it's been a good relationship. And so in particular, and RFK, you're talking about that when we talk about like customizing the cable, we did need a custom cable here because if nothing else, we need to customize the lengths. And Doug, I can't remember who coined the term squid cable. I don't know if that was, I think it might have been you coined that. I'm not sure who did, but I know that we all latched onto it pretty quickly because it does, if you look in the photo album, it does look like a squid. And it is in part because we've got all of these different lengths because each cubby is a different length away. And this is the kind of thing that would be, when you're racking stuff on your own, it's a real pain in the butt to get all this stuff right. But because we can rack these cubbies together once, we can get all of these cables at exactly the right length. So Doug, do you want to describe a little bit like what the squid cable is and what went into kind of the design of that?
Sure. So the squid cable, I guess the entire cable backplane is made of 16 plus 2, 18 of these squid cables, 16 plus just a kind of a single link for the PCIe. Each of these squid cables individually has a connection that goes to the sidecar, the network switch, and fans out to four smaller connectors for each gimlet, each server. So all in all, there are, like I mentioned, 16 cables in the system, and each network switch sidecar needs to talk to each gimlet server. So in kind of laying out the initial 3D CAD concept, we tried to come up with a way to make these connections without using 16 unique cable SKUs, part numbers. So one of the CAD images in the photo album has kind of a view of the breakdown of how we split these cables apart. So basically left to right are copies viewed from the back of the rack. And there are three kind of unique part numbers or SKUs for the cable squid that we're using. So the thought was we didn't want to have too many, such that if something did happen to get damaged, that a service personnel would need to stack 8 unique cables and bring them and swap them out. So three unique cable lengths seemed like an appropriate workable number in the mechanical design. So there's kind of a short, a medium, and a long. The shortest ones from the sidecar, the network switch connector, to the gimlet server connector is 1 meter. The medium is 1.25 meters, and the longest is 1.5 meters. So they're different enough such that when you hold them side by side, you can tell that they're different. But at the same time, there's enough spread there that you could basically cable the whole rack with just 3 unique types. So there are a couple of locations where there's a little excess length that we just kind of have to hang to the side. But I would say for the most part, we weren't too terribly restricted in choosing basically 3 kind of unique part number types.
That seemed to have worked out really well. And so as we were putting this thing together and getting it together, I mean, I'm trying to recall some of the friction that came when we actually got this thing fully cabled up. But I came together pretty well, but I know that assembly was definitely a challenge. Do you want to talk about that at all?
Sure. So yeah, going from the concept sketch from Arian to a 3D CAD model, which we did put a fair amount of thought into to try to get a reasonable approximation of what we wanted the lengths of these cables to be for prototype purposes. Again, so that we didn't certainly have a cable too short for our first spins, given our kind of desire for minimal churn. And then from the 3D CAD model, to physically integrating it into the prototype assembly, there was a lot of learning opportunity there. So, everything looks neat and collected in the 3D CAD model. Obviously, we understand that's not always going to be the case, or never
Right.
going to be the case. There is an image in the chat that's kind of, I think I named it spaghetti, that's got basically the pre-build of the cable backplane integration into the rack, where there's just all these cables coming off, and to try to discern one from the other was fairly difficult. So that was part of the challenge in evaluating our early and our next stage prototypes, was how to best route these such that they can be repeatedly placed in a consistent manner without damaging them. So again, with kind of the rat's nest, as we put this together for the first time, there were definitely a lot of points of feedback where we realized we could do certain things better, both in how the cables are bundled and how they are routed and assembled, that led to future design iterations that are forthcoming here.
And so in terms of the damage, what kind of damage are you concerned about with? I mean, it's not, on the one hand, it's not fiber optics, so you're not worried about the cables snapping. But on the other hand, like bend radius is an issue, and you've got, what are some of the kind of the points of damage you're concerned about?
Yeah, so bend radius is actually fairly forgiving on this cable type, within reason. So these are twin axial differential pair cables. So Samtec says there's a good bend and a bad bend. Basically, if you bend the cable such that both of the wires inside of wires of the pair bend the same, it's a good bend. And if you're bending them kind of against themselves, that's a bad bend. So we made sure as much as possible in the mechanical design that we were routing these cables with good bends. Now, that wasn't completely possible without a few twists and turns, but to the best of our ability, we routed these cables in the design with the best bends we could. So the minimum bed radius on the bundle wasn't terrible. Individually, where these cables, these twin axial cables, exit the connector, in between where the connector ends and the kind of bulk jacket, the black jacket starts, there has to be a gap, basically, where just this Teflon coated blue wire is exposed. And this Teflon coating is very thin and easy to mar. So early on in the mechanical design, we had a few metal on Teflon contact points in the design that we had to eliminate and replace with plastic in the DVT build designs. And that drove a few design changes. And then more recently, we've, with the crew out, I don't know, a month or so ago, we found some better ways to better kind of bundle and collect these individual cables, so that there was less opportunity for this rat's nest, this spaghetti that we see in some of these images, where 4 cables from one squid just totally commingle with 4 cables from another squid. So better bundling techniques, more kind of defined assembly methods, and all of this kind of leads to reduced potential for damage at manufacturing production. And certainly, I believe the more consistent and repeatable the location these cables are to each other, the more consistent and repeatable our electrical performance with regard to EMC should be as well.
Totally. It's all right. So, and I want to actually go into this issue that you all resolved recently, because it was, we've had a couple of issues that have been harrowing, and one of them certainly was in these early DVT racks, and in fact, the rack that was, and okay, you're going to remind me, because in my recollection was, this is it was the rack that was going to go to compliance, and we were seeing pretty disconcertingly high failure of and these cables didn't seem to fail transiently. It seems that they were, by the time because we're very much kind of putting this system together. We're building the system as we're in our DVT builds. And so a bunch of the validation that ultimately that is going to be done, or is being done there in Minnesota, Doug, was being done in out here in Emeryville. So this thing had already been kind of shipped out, and we discovered I'm trying to remember, you and Arian had discovered that basically that a whole subset of cables needed to be swapped out. And as I recall, that was a late night brain transplant right before compliance. Am I remembering that correctly?
Yeah, that was not cool. But we did it because you gotta. But you're gonna go to EMC. You want all your sleds to turn on, or we'll have it, or have network, or be able to have everything. I mean, this is the nervous system of the whole rack. So, like, you lose a cable going somewhere, and you've lost those sleds. And you don't really know why, because at the time we didn't have the infrastructure to like test these fibers on their own. But so what we had to do is, you identify which sleds don't, come up, and we can on sidecar, we can get pretty detailed on, what pairs are not working. And so that's helpful in that, and if when you're running at 100G, it's actually kind of difficult to tell, exactly why it's not working. Because it doesn't necessarily mean there's no continuity. You could have degradation in the cable due to like the fact that you're bending it up a bunch, and that would obviously cause a really high speed link just to fail. So you don't know, like you could do a continuity test and it would be fine, but that actually doesn't tell you why it's if it's broken or not, or which cable it is. So you have to go into the sidecar and have it probe which diff pairs are failing, and then from that we had to map that back out to our handy like cable or pair map that Samtech did, which is like this 3-page Excel spreadsheet of like how do you get from a single diff pair through to where it goes onto what cable and then to what sled. It maps all the way through, which is, again, they didn't have to help us through all that, but I know Arian and Jonathan sat there, I think, for quite some time and got that all figured out, which is, bless them. And so we did that. We figured out which squids had to come out, so we had to cut the entire backplane out, because at the time you couldn't just pull one bundle out all at once. It was all kind of wrapped together, and you can see in some of the pictures where it looks like this weird nest of stuff that just kind of like goes into the center and splits out into a bunch of different directions. And that's the old way it was, and that in its disorganization, that's kind of where these problems arise. But you see these zip ties that are like holding us all together. You have to cut everything out. So you take the whole thing apart just to replace one piece, which not cool. But so we did that.
Well, there was this moment where we were here in the office together. It was you, Arian, and me, and you and Arian now know exactly what needs to be replaced. But we are running out of racks to actually we don't actually have the necessary cabling. And then someone was like, wait a minute, we have what we've been calling the showcase rack, which, Doug, this is one of the early racks that you all put together, that it has a cabled backplane, but not necessarily much else. So we realized that we actually have the cabling from that showcase rack. And as I recall, I mean, I think that's where you ended up getting some of the cabling from, right, for compliance?
Yeah. So we kind of identified that, like, well, this is the same gauge and it has all of its cables, and we haven't done anything to it, so they should all be okay, assuming we didn't break it the same way we did the other one. Like, well, there's only one way to find out. So
under the knife.
It got the multi-tool out and sat down on the bottom of the rack. I think at that point it was like 11 or something p.m. and Ari and I were like, well, I guess it's beer time. And then just start cutting the thing up. We're like, okay, pulling the cables out, go to the other rack, like cut that whole thing down, because you got to do it twice over. And while we're at it, we might as well organize the back of that one so that we can shut the doors and it'll all look good, and hopefully it would help with how things radiate. So we cut all that up too, pulled the old ones that we knew were damaged out, put the new ones back in, rewired, zip tied the whole thing, fired it up, and thank God.
It worked.
Yeah, I don't want to do that twice.
Yeah, right. Exactly. This is because this is always this challenge of like you're trying to do everything all at once, and it's hard when I'm sure you were very relieved. I mean, I guess it feels it could have been just as plausible to be like, and now nothing works. But it was, um, we were able to get this. So that was the rack that needed to go to compliance. And this is, several months ago, we talked about all that when we regaled from compliance. But we had this issue of why did we have this high dropout rate? And RFK, that's what you went back to Minnesota to work with Doug and Jonathan from Samtech. And Doug, I gathered some members of your team as well. With what can we, because our hunch, and Doug, I think it was your hunch as well, is like, okay, this is something that we're doing as we are assembling this is resulting in some damage. Was that the hypothesis going in?
Yeah, I believe so. So like I mentioned, the design itself, I I didn't believe had any issues that were nominally causing these problems that we were seeing, but in the integration, the assembly, there were plenty of other opportunities to damage these connectors, these cables, which we believe was the source of the issue here.
I mean, it's tough to root cause that kind of stuff too, because if you're going through
Totally.
assembly and you have different people trying to do different, like install different components, you get into the realm of the random, so it's handling is such a strange way to in order to narrow that down, it gets pretty difficult unless you have a very specific install process. And on these, not really at the time.
Well,
Yeah.
and when you're building something like this, you're not just designing the thing; you're also designing the way you build the thing. I mean, it's like very much part of the development process is how you manufacture it, how you assemble it. And I mean, there's a lot that needs to be kind of debugged and understood here, trying to understand where these things are coming from. So, Doug, it seems like the kind of the first order of business, at least from my perspective, the first order of business was understanding how are these things damaged? And Samtech was able to turn around pretty quickly and tell us what exactly happened.
Yeah, so I believe they were able to look at our assembly process and kind of determine where the issues were coming from. So, stepping back, it's just a little bit. The showcase rack, I physically built the cable backplane on. I had every intent of building the cable backplane on these these other two racks as well, and became ill. So somebody else had to do it the 11th hour. So we were able to kind of get some operator variability, which is absolutely a part of every manufacturing process.
Totally.
To
Yeah,
ex-
I think it's
to
a
ex-
positive.
yeah,
Yeah, exactly.
to expose these issues, which thankfully were able to be corrected. But if there's one thing to gain from it, it's that. So so we basically walked through with Samtech on site the assembly procedure that we had, and I guess it was determined there were a couple of kind of key points within the assembly that needed some attention. So nearest the connectors on the sidecar, the network switches, there was a fairly tight bend where a tight gathering of these jacketless, kind of the exposed Teflon coated differential pairs, where there was some marring happening. So that's kind of an action for future consideration, both in the design and the assembly procedure, to ensure that doesn't happen. And kind of taking a step further here, and it was both due to kind of Samtech's um, uh, assessment and RFK's kind of mention of the pain of replacing these, that we determined that there were some different bundling configurations that we could put forth that would better keep like cables together, keep them from kind of going astray,
Hmm.
and getting potentially damaged elsewhere, and um, kind of staying together as a kind of a cohesive bundle. So there was a lower potential of damage.
And so then can you tell me about this thing that you 3D printed on site to help you assemble this? I'd love to understand that. We've got the slide that's got kind of that green the green jig at the bottom. Could you describe that, Doug?
Yeah, so there's a couple of things there. So we tried to kind of quick turn 3D print in house as many manufacturing aids or tools or fixtures as we could. both to kind of assist in keeping operators hands free and for kind of error proofing the potential for in the assembly. So these cables are keyed. They're with small plastic tabs that should prevent you from putting them in upside down, but they're not very pronounced. So if if you're not careful, you can put these connectors in upside down into this cartridge, and I've done it myself a couple of times. Luckily,
Yeah.
we're only early on prototypes. The failure is catastrophic. The guide pin of the cable completely destroys the connector on the server sled. The
Oh,
signal wafers on the server sled. So that's one we found out early we want to prevent. So that was one where again we found it out on some rigid copper clad boards that were for purely mechanical purposes,
Wait,
non-functional. But
oh
Doug,
wow. Now,
is this a steel spike effective like hammering a nail into the sensitive connector? Is that effectively what happens?
that's effectively that's exactly what happens. Yes.
That's,
that must have been an eye opener. I was like,
yeah, you
okay,
pull that out, you're like, I think I know what
okay,
happened here.
Well,
Yeah.
if you're ever in the office, just like go to the back of one of the gimlets that we're not using anymore, and you can just like press in the tiny, like they're feathers of gold little tabs that they contact with each other. You can just touch them and be like, oh, those are like quite light and easy to move, and then just jam a screwdriver into the back of it, and
that's right.
think about
Simulator.
Yeah,
So that was very high consequence. Interesting.
that 3-to-1 mechanical advantage on the lever is handy for correct use, but
That's right.
you almost don't even notice that you destroyed the thing when it's incorrect. So yeah.
Right.
So we
Okay, so
found
you
that early.
definitely want to avoid that problem. Yeah,
Right.
that's a good one. Yeah.
So as many fixtures as we can come up with to prevent incorrect assembly, we tried to implement for our build here. And again, to arrange things on a bench in a kind of consistent and repeatable method so that the end isn't hanging off of a table or anything else that could put undue stress on these connector systems. We try to implement as much as possible here. So again, these are kind of early prototypey fixtures and nests, but they'll kind of feed into more long-term production type procedures and tooling.
Well, and I love the use too of 3D printing because, and Doug, this is something that you did a lot. I mean, there are a bunch of things that you were 3D printing in house for us. Think about the air shroud around the M.2 connectors that you all designed. I mean, this, and I'm sure actually a bunch of stuff I'm unaware of, but this is something that is a tool that has clearly been, I imagine, transformative from a mechanical engineer's arsenal.
Oh, absolutely. Yeah. So, to be able to come up with a concept and turn it around and have it the next day is huge. I mean, we had our 3D printers running almost constantly to try to, iterate and learn from each one. So this particular green fixture that we used for the assembly here, Brandon, one of my counterparts here, designed that. And, it's one of those things where we designed it, didn't like how it was, and we had a new one designed and printed the next day. So it's just, yeah, game changing for turnaround time and kind of cycling of these types of designs. So in the end product, there's a few pieces that are 3D printed. It certainly has its place in the product design, but in terms of early prototypes, prototype evaluation, tooling, nests, that sort of thing, where normally we would have to machine that out of a piece of Delrin or something similar. We can learn a lot from these 3D printed pieces. And I know the Oxide team embraces that as well. You've got a few of your members there that have their own printers that make their own tooling as well. So,
Yeah.
again, it's widespread. We use it
Well,
well to our advantage.
yeah, and I just think it's one of the things that we've definitely said before here is that people like to dismiss hardware as hard. Hardware is hard, but it's also easier than it ever has been. And this ability to take these kind of quick turns from ideation to something physically in hand that you can iterate on, and then especially for a fixture like this, this is like a fixture that you're using to assemble the product. So, this is something that the quantities are low enough. I mean, this is presumably something, you're presumably not going to 3D print it for what we're going to use on the line, but you could. I mean, it would be certainly great to be able to spend quickly on this. And then, so because you had Samtech on site, with Jonathan was on site, and RFK, you were there, and this was, it sounds like it was really helpful, I gather, to have everyone kind of there at once, physically doing this together, because yielded what sounded like a much cleaner assembly.
Yeah. Well, it was really good to have everybody kind of see the same problem in real time, and then particularly Jonathan initially describing kind of like, oh, these are this is the kind of behavior and bending that we don't want to see, and then what is also acceptable, and then kind of how the fibers float inside the Teflon, along with the dielectric. So it was clarifying in that he identified a particular type of bend that we are doing, or we're doing, pretty explicitly as it routes out of the sidecar. So like the center of those photos, you'll see the largest connector where it kind of funnels out into the center and then goes up or down. That's a 90-degree bend with a twist and then a 90-degree bend. And what that'll do is that'll cause like an uneven push and pull on the connector side in that little cartridge. And so it's like, that's a bend that you don't want, or versus like you can have like the cables, if they were allowed to float, they could kind of bend together in such a way that they wouldn't be pushing and pulling against each other. And so, that's an okay thing to do. And when we got in there, we kind of looked at how these things were taped up, and how there was a lot of math added by this sheathing it's the black sheathing that goes around these cables. And kind of see how they pulled, and like if you remove the tape and then added the sheathing a particular distance depending on the size of the cable in order to decrease the mass, how you are able to bend these things more safely and allow them to float in such a way that they're not affixed at one end when you try to bend it, which when it's affixed to that tape, that you'll see like at the tips of the cables, it's all bonded together. We got rid of that. You create and I'm not a mechanical engineer. There is a word for this. The point where it can no longer move and the rest of it moves, and it causes uneven forces on inside and outside strands. I don't know, but there's something for that. Anyway, we were able to see that problem and run an experiment. We're like, well, let's cut some this sheathing of the lengths that we want, remove the tape, and see how much mass we can cut down. And after we all kind of got together and did the process of painstakingly removing all that tape, I mean, oh my god, my fingers. But yeah, then we got to one of the pictures where you'll see it's just these kind of 4 tubes that come out instead of this nest, and they funnel very neatly up and down the sides of the rack, and there's a serious decrease in the amount of mass that we have to deal with, and it makes the assembly and install way easier. There's only like 3 or 4 different cables, I think, total, and I mean, it's just visible. You can look at it. It's so clear how much better that is, and the install is going to be repeatable, and you can do it in under 2 hours versus it took us probably like 3 to do 1 in the office.
Right, and you presumably don't need to be Doug to do it.
Right, Doug, you can have other people do it, and so you don't have to do it yourself.
Right. I'm not going to put. Not throwing my hat into the ring, or Adam's. No offense, Adam. I just feel like, actually, no, Adam, you're much more reliably mechanical than I am. We're not.
You're right. You're not. I'd probably take some shortcut. It's fair.
Not quite at that point, but it is really important that you get that. And this cable backplane, because someone had asked, it's like, well, what do you do when this kind of wears out, or how does this fail in the field? This is really designed to not fail. This is actually designed to be with the lifetime of the rack. So we want to be sure that any failure that we might have in assembly, that we find on site, that this is not, by the time this leaves, that we've got something that is going to be really, really, really robust. it's not impossible to replace. It's just, and RFK, you all made it. If one needed to do a field replacement, it would now be potentially possible. But this is not a field replaceable unit. This is really designed to be to go the lifetime of the rack. So it's really important that this thing is actually designed for the long haul, and this is something that is we really wanted to invest to get exactly right. We got that final image there shows the rack after you all had recabled it, and it looks glorious. And so,
Yeah.
so Doug, this must have been I mean, satisfying to get that to get all of this kind of root caused and figured out. I know from RFK's perspective, it was just glorious to get this nailed and to kind of pull together folks from your team and folks from Samtech and their team and work together to get this thing debugged.
Yeah, absolutely. To have so many different, parties and perspectives from our design engineering group, our manufacturing group, Oxide service representation, and the cable manufacturer was great. I mean, we really, I think, hit this on all fronts, and the result moving forward should be a much more kind of consistent and repeatable product integration of this cable backplane.
That is absolutely awesome. And I think it just highlights that when you're doing something like this, and something I know we have really emphasized is finding folks that want to build this with us, who really share our perspective. And Doug, you and your team at Benchmark certainly do, and the folks at Samtech certainly do. And it's been you really see the results here because when something doesn't, when something needs to be kind of figured out, you really need everyone together to figure it out as a group. And this is just a lot of fun to see, and just could not be on something more important in terms of this cable backplane, because this thing, again, we live or die on this thing, as do our customers. So, well, this has been great. I know that it should be said that Adam is from Connecticut, and you've normally we think of Connecticut as being merely New York or Boston, depending on which part of Connecticut you're referring to. But actually, tonight, Adam, Connecticut stands on its own 2 feet as your Huskies are in the NCAA finals for basketball.
Yes.
I hope you put a lot of money on them being in the finals.
I didn't. But usually it ends in heartbreak, because I always pick them to win, every tournament, and it only happens occasionally, but it does happen occasionally.
So, I actually went with my sister puts together a larger bracket with the extended family. So of course the stakes are extremely high, because I actually need to make sure that I beat my sister, or if failing that one of my children does. We just can't have my sister winning the broader family pool. Not that I'm competitive at all. And I did my all Oxide bracket with I took the schools that this is kind of what I've done every year. Let's just say that there's a Texas Tech alum among us that I think Texas Tech didn't even make the tournament this year. RFK, or I would have, but
that's okay.
Texas Tech did not have the opportunity to disappoint me the way we have many Purdue alums here at Oxide, and not to add insult to injury, but let's just say go Huskies is what I'm really trying to say here.
Go Huskies.
We digress.
So
Huskies good.
Right. And by the way, that family pool is being won by my brother-in-law's nephew. The 6-year-old has picked UConn to win. So this 6-year-old is going to walk away with it. I don't know if this is some like March Madness child prodigy. I'm not sure what's going on. But,
or if it's like the octopus that was picking the World Cup winners. Either one.
I think it may be the World Cup winning picking octopus. Yeah, I'm going with the octopus theory. Or I like dogs is the other theory that I was going with. I mean,
That's right. A lot of dog mascots. Yeah.
A lot of dog mascots, and I'm going with that one. But regardless, we want to make sure that you get to the Huskies in the finals here. But Doug, RFK, thank you so much. This has just been so much fun to watch. Doug, it's been so great to work with you and team. And again, I hope folks get the chance to feel this thing. And if when you make physical contact with an Oxide rack and you're thinking to yourself that, boy, someone really thought about the mechanical design here. It is Doug, it is you and your team who really did that. And thank you so much. I hope you're proud of what you built here, because it's really fun to watch it all come together.
Oh, absolutely. It's been great. Yeah, it's been a pleasure working with your team.
Awesome. All right. Well, I think if you don't mind, we may have to have you back on a couple of other mechanical topics, because we got there are a lot of mechanical bits in the rack here, and there's a lot that you and your team. Well, at some point, we'll have to talk about the moment arm crisis. I don't know, Adam, if you it's like
you know what? This is another one where I've heard mention of the moment arm crisis, but just like some of these cabling issues, I had to wait for the episode to find out all the details.
Exactly. Well, we could do an entire episode on the sidecar heatsink. That thing, the monstrous sidecar heatsink.
Oh Lord.
But that will wait till after the Huskies win the national championship. So, on that, thank you very much, everyone, and we'll see you next time. Thanks again, Doug.
Pleasure's all mine.
Thanks.
Thank you.
Take care.
Thanks, everyone. Go Huskies.